Today we are going to talk about deep learning for natural language processing and parameter optimization. So I'm going to talk about the NLP part. So we will overview some of the typical tasks in natural language processing, and we will discuss how those can be solved by more traditional machine learning techniques, including different classifiers, and I will also introduce you to the idea of language models that have been used traditionally in NLP for quite a long time. Then we will discuss the deep learning framework and how it actually helped to facilitate so many applications in natural language processing in the recent years. And then we will also discuss the parameter setting and why it is important, at which point I will switch to Valentin, and his part will be about parameter optimization. So first, what are the typical NLP tasks that we address here? So NLP as itself stands in between those other areas, so it involves a lot of machine learning techniques. It is driven by the advances in machine learning. It is also quite often considered to be part of artificial intelligence, but as such, it is a field in computer science and computational linguistics. So I will give you some examples. Information search. Whenever you search something on Google, it uses NLP techniques to actually find the relevant information for you. Machine translation is another example of NLP technology. Spam detection. Nowadays, you probably don't see much of those spam emails coming into your inbox, thanks to NLP technology. Spelling correction. Whenever you actually type something, say in word processor, it would highlight the incorrect words for you. So this is driven by NLP technology as well. Sentiment analysis, predicting whether a review on a movie is positive or negative, whether it is saying something good about the movie you have seen, is also driven by NLP technology. So let's now see how those can be solved by more traditional machine learning techniques. Let's, for now, just focus on two of those, spam detection and sentiment analysis. We will see that those are essentially quite similar tasks. In each of those cases, we are talking just about two classes that we want to distinguish between. So in case of sentiment analysis, we want to predict whether something that is written in natural language has a positive sentiment or negative sentiment, whether a review about a movie, a restaurant, or a book is positive or negative. In terms of spam detection, we want to distinguish whether this is a spam email or what is called ham email or a valid email. So what we can use as features in this case are just the words that are used in, say, reviews or the emails. So we can train a classifier, just a simple binary classifier of your choice, say naive Bayes or SVMs or decision trees, which are going to rely on those features, and then we can apply them to new emails or new reviews and predict either the sentiment or the class, whether this email is spam or ham. So this is kind of as simple as that. Now, what about text prediction? So this is a good example of what text prediction does. So when you start typing something on your phone, the system would predict what the next word is likely to be. So on the left, you see the output of the system that used these more traditional techniques. On the right, these are the new advances and the new technology that is driven by the neural network. So we will look into the neural network part a bit later. But now let's try to understand how this text prediction works in the basic case. So it has been addressed for many years, and the technique it relies upon is called language modeling. So what we want to do, given a lot of data, we want to learn what are the most probable continuation of a phrase, given some context. We usually would just use several words before the particular word that we want to predict. So for example, we see just the two previous words, the context, at them. We might consider the following continuations. It might be a moment, it might be and, it might be same, or it might be was. Who thinks it would be was? Obviously, it wouldn't be was. Why? Because we've never seen that in the actual data. So if we just use the data that we've seen before, and we calculate the probabilities from this data, we would be able to predict that something like was is a very unlikely continuation of this phrase. This is done by calculating how many times we see a continuation of this phrase divided by the number of times we see the context in general. So in that case, we would be able to predict that a continuation like moment is much more likely than a continuation like was. So that's how this system would work. If we want to predict the probability of the whole sentence, what we do, we use the chain rule in which case we just take the probability of the first word, then we take the conditional probability of the second word, given that we've seen the previous word, then we take the probability of the third word, given that we've seen the previous two words, and so on, and we multiply them. Now, this system works reasonably well, but it also has a number of limitations. So say we've looked at this example with at them, and the possible continuations at the moment, at the end, at the same, which are all quite probable, because those are very frequent phrases. But what if we see a bit of the context before that? What if the actual context in the whole phrase, in the whole sentence, was I'll meet you at them? At that point, we know that all of those three possible continuations are now not very likely given the previous context. And the traditional language models that were limited by this previous context, where we need to specify how many words before we need to look to calculate those probabilities, are limited in that case because we can't predict the most probable continuation given a lot of context before that. So this is what neural networks help us to overcome. This is one of the limitations that they actually solve. And they would be able to predict that more probable continuations after this broader context would be, say, airport, office, or hotel. So you would see those suggestions in your phone because of these new advances in the technology. Just to give you a flavor of what their neural networks are capable of, I'll give you a couple of examples. This was actually published as a quiz in New York Times last year. So they collected the output of some neural network-driven applications that either produced prose or novels or poetry or news articles, and they also gave some examples of what was written by humans. And they asked people to guess which ones were written by a machine and which ones were written by humans. Both of these were written by a machine. You can check, those are the links to the actual algorithms that created this. The one on the left was written on the basis of Shakespearean text, so the machine just was trained on the Shakespearean text and produces something in a very similar style. If you just look at the years when this was done, it was just within the last couple of years, so to say. So it's quite novel algorithms. Now, what is it all about? If we look a bit at these previous approaches, the more traditional ones that we used, as we said already, with the more traditional ones, we ran into these limitations because the previous systems were not able to take long-term dependencies into account. If you also think about how the probabilities were calculated, so we need to always rely on what we see in the actual data, and we need to specify the previous context. And even with a very small vocabulary of like 1,000 words, which is much smaller than a vocabulary of an average adult person, we would need to calculate the probabilities of 10 to the power of 9 different 3-word sequences. And most of those we wouldn't see in the actual data, so that would make our probabilities very unreliable. So that's just some of the limitations of those systems. Another thing that we need to keep in mind is that actually with those more traditional systems, it is harder to solve tasks that involve a lot of variation. And language is a good example in that case. Because what we want to ultimately do is we want to learn the representations of the similar objects, even if they sometimes seem to be quite different. And at the same time, we want to differentiate between the objects that are dissimilar, even if in some contexts, we might see them together. So to give you some examples, in terms of the visual data, you see the area that is highlighted in green. So those are all the representations of the digit 2, even though they might appear a bit different. So it would be quite hard to describe what makes 2 a 2. But they're still all the representations of a digit 2. At the same time, you might see that some of the other digits might look quite similar to 2. But we want to be able to differentiate between them and say that those belong to a different class. In terms of the language, it would be a similar case. So we've looked at these examples with airports and hotels. So we want to say that those belong to the same class, even though we might have never seen them in the same context, so to say. But at the same time, we want to predict that, say, moments is a representation of a different class, even though sometimes you would see it in the same context. So we want to keep some of those examples apart, and we want to combine some of those together, which would make sense to a human being, but how would a machine do that? So that's where the neural networks and those recent advances helped a lot. To give you a bit of introduction into that, artificial neural networks are algorithms that are inspired by biological brains. And the idea is that they try to model the neuronal responses in the brain that are associated with various stimuli. So when we use the term deep learning, this just refers to using many hidden layers in these representations. So connecting all the different neurons in various ways. And then these algorithms, as we will see, are well suited for this unstructured and unlabeled data. Many recent advances were driven by these algorithms, and some of them we will overview today. So the artificial networks are based on the idea of artificial neuron, which itself is quite a simple classifier. So it takes an input, which is just a sequence of features describing the data, which are represented as a vector. It then produces an output in terms of a prediction. And each of those features in the vector are going to be weighted in a different way. So in a different way, there will be a weight assigned to each of them. And then the correspondence between this representation in the hidden unit and the output is going to be learned using a nonlinear function. So the representation is simply like that. But then when we talk about the networks, they are going to connect many different neurons, and they are going to use a more complicated structure. But the idea behind the recursive neural networks would be that it is able to store the information and pass it from one hidden unit at one timestamp to the next timestamp, and so on. So it is going to keep the information for us, and this is what makes those algorithms powerful. So another idea that is important to keep in mind is it uses these nonlinear functions that help to approximate their output. This is the math behind these networks. So we are going to use different types of weight matrices to basically help us to pass this information through the nodes. And the nonlinear functions that are used there would be, for example, sigmoid or this tangent function as is here. And we are going to learn those weights in a way that when we produce the output by our neural network, we are going to compare this to the output that we want to produce, and we are going to backpropagate the errors, this way setting the weights in the correct way. The problem that we might run into with this is called the vanishing gradients, and there is a trick around that. So if you want to learn more about that, look into the long short-term memory units. These are some of the aspects about the neural networks to keep in mind. So the powerful algorithms and the power of this as applied to natural language processing tasks lies in the neural networks that helps to incorporate all the various types of information in the very same representation. So people in recent years have showed that you can use data and information that comes from many different languages and combine them in a single representation, which helps to learn more realistic representation of meaning. It is also possible to actually involve the information from visual signals, which makes them even more powerful. So basically, this ability to actually create one representation that would be suitable for many different tasks makes them very powerful. So that's why they actually have facilitated progress in many tasks, including named entity recognition, part-of-speech tagging, parsing, and many others. Another topic that is important to keep in mind when we talk about natural language processing and these advances of the recent years is related to word embeddings. So basically, word embeddings are the representations of the meaning of a word for a machine. So how are we going to represent a meaning? We are going to represent each word as a vector in high-dimensional space, where each of the dimensions in the space is going to capture some aspect of this meaning. So for example, as we said, our goal is to represent similar words with similar meaning with some similar representations. So that means that we want to represent the words that share meaning somewhere close to each other in this semantic space. So many of the dimensions of these multidimensional representations should share similar values for similar words. So if, for example, we say that airport and hotel from our previous example are similar to each other, they're going to be close to each other along the dimension that, say, represents buildings. So that's why those models are called distributed models. So it's as if we distribute the meaning of the words across different dimensions in this very highly dimensional space. So we are talking about hundreds of dimensions here. We're going to learn them from the data. So just to give you an example of how this might look like, imagine that the word airport is represented as a vector which has some values. Say we now represent just 3 dimensions, but it's going to be like hundreds of those. and same for hotel, for example. And some of those values will make these vectors really close to each other. There is a tool that helps to visualize that. So this is called t-SNE. So if we look at the representations that are learned with these applications, we will see that in some parts of this semantic space, it is highly dimensional space, but if we just look at the representations of those words in that, we would see that the names of the countries and nationalities lie somewhere close to each other in this space, and so on. So different parts of the space will keep the words that share the meaning or have similar meaning close to each other. And this is what helps us to actually interpret them. So now going back to this question of artificial intelligence and how it is related to NLP, today we are going to just focus on some of the applications that I find the most exciting. So they are related to communication agents, to chatterbots, and language generation. So these are all the applications that were driven quite a lot over the past years by these new technologies. And this actually makes the state of the art in artificial intelligence quite close to how humans reason about the world and how humans express themselves. We're going to see that in the recent years, people showed how to predict and how to generate text at all the different levels of language granularity, starting from characters and proceeding with words, and even at the level of phrases. So I'm going to just talk about these three works, but there are many more. So if you try to visualize what it's like going from a very fine-grained level from the characters and predicting the next character on the basis of the previous ones, proceeding with prediction of words on the basis of previous words, and ending up with whole phrases and whole communication acts using the previous communication in this sequence. So in terms of the word level prediction, the goal of this application would be using the previous context, predict the next words, something similar to what we've seen with prediction on the phones, for example. But this time we're going to use the neural network, and our goal is to optimize the vectors that represent the meaning of the words together with this system so that the vectors that we end up with are going to be good fitters for this model in general. Given that we have the vectors that represent the previous words, say up to 3 previous ones, we're going to feed them into the neural network, and we're going to produce the output and then calculate the probability of the most likely words that would follow from that. Distributed word representations were used quite widely for this nowadays. So this is based on the work by Mikolov and colleagues back from 2013, where they showed with 2 models how to learn these representations of a very high quality that are widely used nowadays. So the original task that they present in this paper was in predicting the words that would stand in a similar relations to each other. So that, for example, we know that if France is related to Paris with some kind of semantic relation, if we give the system a word Italy, it would predict that Rome stands to Italy in the very similar relation. The same could be said about syntactic relations. So if, for example, we say that words big and bigger are somehow related to each other, and we give the system a word small, it would predict smaller. So basically, the 2 models differ in terms of how they predict the word vectors. So the continuous back-of-words representation model predicts the word from the context surrounding these words. So we use the representations, we use the vectors of the words that surround the current one. We feed them into the network, and we predict how the vector for this particular word would look like. And the second type of model, the skipgram model, does some words complementary task to that. So it actually tries to predict the surrounding word representations based on the representation of the current word. And then when they applied those representations to the task at hand, that's what they showed, and those are the results that they got. So basically, given the machine a pair France and Paris, and then asking it to predict something on the basis of Italy, they would get Rome as the answer to this question of analogy between the words. If the system is showed something like Einstein scientist, for Messi it would predict that it is a midfielder, and so on. So basically, the system learns these subtle relations between the words without being told specifically what the type of relation is. And this is possible to do by just using the representations of the words in the semantic space and applying simple algebraic functions to that. So we just take a vector for one word, we detract the vector for another one, we add the vector for the third word, and we get the results. And by just measuring where in the semantic space the resultant vector lies, we're able to predict what the outcome should be. Now, in terms of the more fine-grained level, prediction of the characters on the basis of the previous context. There has been some work that looked into that as well. And obviously, a very useful application of that would be to help, say, people with disabilities by providing them with tools where they can basically type by just suggesting them what the possible continuation would be on the basis of what they have typed so far. In that case, again, we're applying neural network. We use this time the previous characters as context. And a clever idea behind that is that basically we also want to condition the next character on what has been said so far, and we want to share the information between the different parts of the words that would likely predict a similar ending. So for example, we know that an ending ink is quite probable after both fix and break. So what we want to do is to share the representation of both these starts of the words in the system. And then if the system says that the next possible character is I, it would with high probability predict the next character as N. So what they showed is that the conjunction of those two things in their system, their start of the words and the shared information between those starts and the next character, produces with higher probability the more likely continuation of the words. So this is the output. And if you just read through that, it might not make sense altogether, but if you look at each of the sentences, you will see that they both use rich vocabulary, they are grammatically correct, and they might even seem to be logical and sensible. And remember that this was generated just character by character. So they didn't use the words in total. They were predicting character by character. And then finally, there has been a lot of research looking into these dialogue systems and communication agents and chatbots. So basically, we want to predict what the next phrase as a whole would be, given the context that is conversational context. In fact, this is a continuation and a sequence of the phrases that have been produced so far. So there is a lot of work into that. We're going to look at just one of the applications because it's impossible to overview all of them. So this system generates responses word by word, but at the same time, it uses an hierarchical structure that is going to condition what is the most likely phrase given the conversational context so far. So if you think about that, this now approximates a cognitive system similar in its abilities to a human being, because it uses natural language understanding, reasoning, decision-making, and natural language generation as integral parts of the system. So the model now is going to use two types of representation. So obviously we want to condition the next utterance as a whole on the utterance that has been produced so far. And within each of these utterances, we want to condition each words on the words that have been produced so far. And we can combine both of those in a single representation, treating their utterances as well as words as tokens in this formula. So that's the background of this system. So basically, if we look at the representation in terms of the neural network, we generate one sentence, or we give the input of one sentence, say, "Mom, I don't feel good." It is going to be passed through the hidden layer. The likely output, given that the real system outputs in this case, is what's wrong. And then this output is going to be fed into the network as the next hidden state. And in that case, it's going to produce the continuation of this dialogue, saying, "I feel like I'm going to pass out," and so on. This is going then to be fed into the next hidden layer, and so on. So this way, we will be passing the information about this whole communication through the hidden states in the neural network. And now to give a little bit of real-life example, this Twitter bot was written and published by an MIT postdoc. It uses a real transcript of Trump, and it's either using the data from its Twitter or also the transcripts from the debates and different speeches to actually train this with a deep neural network. And if you look at the output, you may even think that they were actually written by a real person. Again, as with this example that I showed you about the previous system, All of those are grammatically correct. They kind of make sense. So their chances are you would even be able to distinguish between a human-generated tweet and a machine-generated tweet in some cases. So now, some of those papers, they also mention how hard it is to actually train an efficient and successful neural network. So in terms of word prediction, the system was trained on Google News corpus, which amounts to 6 billion word tokens. The vocabulary that they used to create vectors contained 1 million most frequent words. So that means their vectors were of 1 million dimensions. So that's a lot of data, right? So what we want to make sure here is that we balance between the quality of the system and the efficiency and the optimal solution here. So they also tried to train the system with smaller vectors, in which case they used 30,000 dimensions. And basically, there are lots of parameters to think about in that case. So if we think about the word vectors themselves, this is going to include the size of the training data, the dimensionality of the space that we are considering. For the algorithm itself, we want to be thinking about the number of epochs, the learning rate, and all the other parameters. For the character prediction system that I overviewed, the training, the report took several days, and it was actually using 8 GPUs run in parallel. So you can imagine how much effort this actually takes. So if we summarize, we want to say that those algorithms are really very efficient and very powerful, but they're still very expensive and they're still very hard to train to get these really impressive results. So a clever original or first setting of parameters may actually be the trick to the successful outcome. And this is something that Valentin is going to tell us about.
Hey everyone. So this talk is about optimizing hyperparameters. So what are hyperparameters? What are we trying to optimize? Well, if you have a neural network, like Ekaterina described in the previous talk, you're probably going to have many things that you're going to be able to tweak or tune about your neural network. So for example, here I have some inputs, some outputs, and I have some stuff in the middle. But how many layers should I use? Recently, like research in deep learning has made us able to use many layers, but sometimes that means 5, sometimes that means 500. So we have to know how to pick that number. Same thing can go about the number of neurons I could use. Sometimes I'll want to use many neurons, sometimes I'll want to use few neurons. And the issue is that there are many, many of these hyperparameters, especially in the context of neural networks. And so just to clarify, all of these hyperparameters, they're going to affect like how big my neural network is, or sort of the algorithm I use to train my neural network. But then once I have this, my neural network's training is going to happen, and I'm going to optimize the weights of the neural network, and I'm going to get a result at the end. And the real difficulty here is that, well, A, there's no real principled approach, and B, there's so many hyperparameters that it makes neural networks really hard to use as a black box tool. You can't just arrive and use your neural network in a random context. The approach which I'll present will be able to use neural networks in a much more generic way. So the first thing I'm going to talk about is how should you evaluate your hyperparameters? How should you decide whether like 500 layers is good or 50 layers is good? So usually when you evaluate just any machine learning algorithm, you have a training set and a test set. And now the issue is that often the error you report is you train your neural network using all of your data in the training set, and then you look at the test set and you go like, well, tell me what you think is the right answer. You compare it with the true right answer, and that gives you a prediction score. If you were to just use your test set to use this prediction score, you'd end up overfitting the test set. So you'd end up finding some results which are good for the test set, but may not be good in general. So the way people usually tackle this is we're going to have a training set, and then we're going to have a validation set. And we're going to use the items in the validation set to say how good the parameters that we have are. And then we can try many hyperparameters like this. And at the end, once we've decided, OK, so 60 layers is good, we can apply our algorithm on all of the data, all of the training and validation data. We can train our neural network on all of this data and evaluate on the test set. And this way, we'll be able to say, well, this is how well the algorithm does. From here, what are the current usual approaches to tweak this network? So imagine here that this big square is just a space of hyperparameters. I have 2 hyperparameters and I have to pick it. So maybe this is between 5 and 500, and maybe this is between 0 and 1, because those are the bounds of my hyperparameter. So how could I pick the points to say which I'm going to try? One usual approach is grid search. So I just try kind of at regular intervals each of them. There's multiple big issues with this approach, but one very notable and maybe a slightly counterintuitive one is that some of the hyperparameters may be very important, and some may be complete noise. So what I end up doing here is that, say only the horizontal one is important, even though I've evaluated 9 different items, I'm going to end up only trying 3 different values for this. And as the number of hyperparameters that I'm tuning grows, and usually for neural networks it'll be something like 10, this is going to decrease exponentially. You're going to have like fewer and fewer items that you're going to be trying for a similar amount of work. So one approach which solves this and is it'll always work, but it just has terrible convergence property, is random search. You just try hyperparameters at random. You just throw it out. And that works well, and eventually, like statistics tells you, after an infinite amount of time, you'll find some set of parameters which is good. But that time will usually be quite long. One other approach is what people call grad student descent. And the idea is you put a grad student in a room, you give him or her a lot of coffee, and you come back a week later, and suddenly your hyperparameters are all optimized. And then finally, there's Bayesian optimization. Although it's a very old technique, it's recently been applied to tune hyperparameters, and it's what I'll be discussing in this talk. And the idea is that just like the grad student had looked at the different regions, decided, okay, bottom right seems good, and then tried some more hyperparameters over there. Bayesian optimization will do the same thing, but in an automated way. And also, very importantly, it'll be much more patient with it. It'll be able to, throughout the night, try new values for those hyperparameters. So on a very high level, how does this work? We're going to use a probabilistic model, and we're going to be training the model to sort of understand how the hyperparameters relate to performance. So we're going to do 3 steps each iteration. The first step is going to be asking the model, what do you think is going to be a good point? Then once the model has told us this, we evaluate these hyperparameters. And then finally, once we got a result, we feed this result back into the model. So as iterations grow, as we've tried more things, the model kind of starts understanding more and more how hyperparameters affect the performance. So there's one type of model which is used a lot in this context because it's very powerful for this context, and it's Gaussian processes. So Gaussian processes, they have a very sort of a rigorous mathematical background. They're like, if you know what that means, they're full Bayesian. That means they do like proper statistics, and they're not like a heuristic. So the big idea is here I have a Gaussian process which takes a single input and returns a single output. So the input is x, you can see at the bottom here, and the output are these like smooth curves. And what you can do is you can sample from this Gaussian process. You can say like, well, what do you expect is a response surface? What is a likely shape for that curve? And here I only have a single input, but this validates for a multidimensional. So if I had 2, you could imagine like a sort of like wavy thing, and if I had 3, then it's impossible to. What makes Gaussian processes good is that they're very data efficient. With very little data, they'll be able to generalize in a very good way. So here, I've given my Gaussian process a single input. And what you see is that, and then I've asked it, okay, can you give me some samples? Now that you know this, what do you think are some possible sort of other shapes with this information? And we can see all of my samples go straight through this point here, which I've given to the Gaussian process. There's still a lot of uncertainty about what happens before and what happens after. An important point about Gaussian processes, which I emphasize at the top here, is that they're non-parametric. So the idea is, as I keep giving more and more data to my Gaussian process, it's going to remember all of the data. This is kind of like nearest neighbor. In nearest neighbor, you remember your entire data set, and when you have a new input, you compare it to every element. But this is not like neural networks. In neural networks, if you have too much data, you're kind of going to forget about it eventually. So here I've shown some samples that I can get from my Gaussian process. But ideally, we'd like a sort of nicer representation. And the Gaussian process gives you this. It can give you a mean function and a variance function. So here, the big, thick blue line is this mean function. It's the mean value that it predicts for each of the possible inputs. The sort of shaded area is the uncertainty that it has for each of these points. What's interesting is that at every point, it predicts the distribution of that point to be Gaussian, which is why they're called Gaussian processes. One of the really great things about Gaussian processes is that with little data, they're really very good at interpolating between the data in an efficient way. So here we can see we have it knows that around this area, because there's already a measurement, it's very certain about what's going on, and here it has no clue, and this is certain again. So now that we have this intuition of what Gaussian processes are, how can we apply them to tune hyperparameters? Well, the idea is, imagine I only had one hyperparameter in my neural network. And I had been trying, and each of these values that I had tried were values of the hyperparameters. And I had actually observed that here I had a value of 0 on the left, and then I had a value of, I think, -1/4 on the middle, and of 0.5 on the right. And I was wondering, okay, so now that I have this information, what's the next point that I should evaluate? One of the really clever insights, and this comes, I think, like it originally was published in '78, but it's still the best way to do it pretty much, is this idea of expected improvement. We're going to pick a point which maximizes how much we think we're going to improve over the best value we found so far. So far we have 3 values, and this one I said was -1/4. And the question is, well, we want a point which is likely to improve upon it, and is likely to improve upon it by a big amount. So here on the right is the distribution of the expected improvement for the same function. So you see there's no point evaluating 1 or 2 because we already know what these are, so there's no point trying them again. But these values, like around 3 and on the edges, they're very interesting. We should try them as hyperparameters. The big idea, and this is an idea that comes in a lot of areas like reinforcement learning and other sort of control problems, is that we want to trade off exploration and exploitation. We want to go for areas where we're not too certain, maybe they're great, hopefully they're great, but also we want to go for areas where we think, okay, so this is probably pretty good, so I should make sure I find the true minimum in this region. In 2012 was when the first big application of deep learning came around, and there was this paper people now refer to as AlexNet, which recognized cats and dogs better than we've ever done it before. And only 6 months later, these guys published this paper that optimized the hyperparameters of that exact neural network to maximize its performance. And what they found was, even though we had this human expert who'd been tuning the hyperparameters by hand for a long time, they just ran this Bayesian optimization concept for something like 20, 30 iterations, and already they had significantly better performance than this human-tuned one. So here I think like the number is 11, and here we're at 9.5. And at the time, this was like state of the art. Like people battled for like 0.5%, and suddenly they just applied their black box method, and it was 1.5% better. Since 2012, many Bayesian optimization frameworks have been proposed. Like I've shown some here, but there's probably some others which I may be unaware of. So this may not be the best representation. The one by the people which I mentioned in the previous slide is called Spearmint, and it's the one that is often used in academia. So just to recap what's very good about this method, it'll be very efficient at searching this space. So a big issue with training my neural networks is that it may take a day for it to happen. So you want something, you don't want a simple method like random search, which is going to try some random points. Bayesian optimization is very smart about which point it's going to evaluate next. And beyond that, it's just an automated approach, which is always very helpful. And this is the end of my talk then. Thank you so much.